So right now, we're just gonna go back over A, plain and simple, and we're gonna go back over it with none of the stuff that we already put on it. We completely cleared it out, and we're just gonna take a look. So the first thing that you look at when you look at this, when they're asking you, is it basically, which one of these four is it? You're gonna look at it and you're gonna say, well, it's definitely not two of them for sure, right? Because it can't be both, like you're not gonna mix the two up. And it's obviously not a substitution reaction because you're not substituting this bond out for anything. You're actually eliminating that bond and creating a pi bond right there, like that. So right off the bat here, you're not doing substitution, and you know that. And that makes your job now very easy. Now you just have to figure out, is it E1, does it form a carbocation, or is it E2, or no carbocation? So the first thing that we're gonna go ahead and look at is your leaving group. Does this group want to leave? And that is a question that I'll leave you to answer for a few seconds. So Br, or bromide, is going to want to leave this. And the reason why is because bromide actually, so it's going to form this Br, and it's going to have all those electrons around it, right? And it's going to have a negative charge. But the thing about bromide is that it is, one, very large. So yes, it's a negative charge, but think of a molecule this big, an atom this big, that just has one negative charge on it. Now think of that in comparison to fluoride with just one charge. See how much smaller fluoride is compared to bromide? It makes this a lot more stable because you can, or the bromide a lot more stable because you can kind of spread that negative charge out amongst the whole thing. While the fluoride is so small, you can't really spread it out anywhere. That's one of the things that makes bromide a nicer leaving group, is that it's softer. You can spread that charge out a little bit. And the other idea behind that, or something else that you can look to figure it out, is how is it when you protonate it? Well, HBr is a strong acid, which means that Br is a good leaving group because that makes this a weak conjugate base, which is exactly what you're looking for in a leaving group. So it's a good leaving group. It does want to go. Now, the second thing that you need to look at is that hydrogen that's attached to this. So there you go. Now, what is going to be reacting with that hydrogen? Well, this is going to disassociate in solution, right? Because it's a sodium, or a metal, attached to this molecule, which is not going to stay together. It's going to turn into CH3, 3CO minus, and Na plus. And the Na plus is also going to help balance out that bromide, just to add on, and it's going to link it over here to NaBr. So that's totally fine and dandy for that bromide. It is content with leaving. And now that we've got that out of the way, we're going to go to this thing wanting that hydrogen. Now, this is going to want that hydrogen right there pretty badly because this hydrogen is very hard. Just kind of like what we were saying about that fluorine earlier, how it's super small and it's got the negative charge on it and you can't really spread it around. This hydrogen's like that on steroids because it is even smaller, but it's still negative. It's still that super small negative thing. So this is going to attract to that hydrogen very quickly. So from there, you're going to say, well, it wants that hydrogen, so it's going to go ahead and take that hydrogen. And it's actually going to form CH3, 3COH instead because it's going to take the hydrogen. Well, look at that. It's actually what's already in solution. So you're just forming what's already in solution, which is perfect. So that's just going to work out. So this is going to be very quick to steal that hydrogen. And this bromide is going to be very quick to leave because it's happy leaving. Well, these are two things that lean us towards not forming a carbocation, right? Because if it were to be a carbocation, then this would be kind of slow to leave, and this kind of wouldn't really, like this nucleophile isn't really going to be so quick to getting that hydrogen. It's not just jumping for it then. That's what would have formed the carbocation. But because this negative charge, that hard negative charge right there on that oxygen, really wants that hard positive charge on the hydrogen, it is going to shoot after that hydrogen very quickly. And it's going to steal it, and it's going to come out here and form CH3, 3COH. And it's neutral. So now it's happy. Because before it wasn't happy with that negative charge on it, but now it's happy. And it's neutral, and it forms what the solution already is. And that's how you can kind of tell that this one's fast. Now, something that you can look at sometimes, but you can't look at here, just because it's in the middle and it doesn't really put you one way or the other, but is how stable is that carbocation. So when this bromide leaves, let's just draw a little thing of what it would have looked like up here, right? When that bromide goes, so you have a carbocation right there. That's a secondary carbocation, right? Because there's a carbon here, and there's a carbon up here. You can't really, it doesn't really lean you towards being more stable or less stable. It's just kind of in the middle. You can't really use a secondary carbocation. It's an intermediate. If it was a primary carbocation, then you could say, yeah, the carbocation is super unstable, so that's going to lean me towards being an E2 because it wouldn't even want to form the carbocation. And on the contrary, if you have a tertiary carbocation, something like this, well, then you would say, well, yeah, the tertiary carbocation is pretty stable, so it might lean towards an E1 because it is content with forming that carbocation and it can stay there because that's going to be stable. That's a stable product. Secondary carbocation is in the middle, so you can't really use it. But primary is going to lean you towards E2, and tertiary is going to lead you towards E1 because tertiary is stable and it'll allow the carbocation to form. And primary is very unstable and it will lead to that carbocation not forming. And that is all of the things that I would look at if you wanted to figure out that this is going to be a monomolecular process or a bimolecular process.